Good morning, judges and audience. We are Project PARSEC, and we will be going over our technical presentation. Before beginning, we would like to thank the organizations which helped us get to where we are now, including Embry-Riddle's Undergraduate Research Institute for funding through the Eagle Prize Fund, as well as the Environmental Health and Safety Department on campus for allowing us to perform our tests on campus, and of course the NIA's gracious funding, which allowed us to travel here today. To begin, our advisor is Dr. Siwei Fan. I am David Clay.
I'm Bruce Noble.
I'm Aiden Kim.
I'm Jacoby Dimby.
I'm Grant Bowers.
And I'm Sanaya Nachani. First, we will go over our introduction and then explain our solutions and analysis, and finally recommend steps for the next 3 to 5 years.
During the Apollo program, one of the many challenges that was documented was plume surface interactions, which caused cratering and ejecta, which put nearby assets at risk of being sandblasted. As we return to the moon with the Artemis missions, this problem will continue to be faced, even more so as we're planning on landing in the same area multiple times. PARSEC hopes to physically mitigate the PSI and provide safer landing conditions and safeguard our assets.
Okay, moving forward to our solution section, I will be introducing our PARSEC solution with a system design overview, then dive into the two main components, the deployment system and then our additives. To select which dust mitigation system we are going to use, we conducted a trade study with 7 different mitigation techniques. We compared these 7 solutions against selection criteria such as lunar lander modifications, technology readiness level, cost, mass, and safety. From this trade study, we concluded that we would use a plume additive deployment system, and then over the course of the past year, we conducted 2 additional trade studies determining what additives we would like to use and what kind of deployment methods we would use. So that brings us here to where we are today. We are here to present our solution, PARSEC, or plume additive for reducing surface ejecta and cratering. In short, the goal of this system is to create a temporary landing pad on the lunar surface while the lander is descending. To accomplish this, we will be injecting a granular ceramic or metallic additive into the plume of the lander via a deployment system installed to the side of the lander. The heat from the exhaust of the engine will begin melting that additive on its way down to the surface, so that when it reaches the surface in an adhesive state, so that way it can conglomerate those regolith particles together to eventually form a larger landing pad. More on that deployment system, I'll hand it off to David.
Our rudimentary deployment system combines 2 different existing concepts to achieve our goal of creating a landing pad below the lunar lander, namely fluidization and thermal spraying. Here is a simplified schematic of what our deployment system looks like, with a gaseous nitrogen 2 tank at the top, the storage for the additive, more on that later, and gas distribution paths for fluidization. This diagram shows what the approximate fluid streams should look like, with the sum going into the plume of the rocket. These concepts were chosen keeping in mind that the deployment system should be minimally invasive to the lander's functions and should be easily applied to any lunar lander or CLPS vehicle. To achieve deployment, our additive must be transported. In general, it is difficult to work with solid particles, especially when transporting them, as they do not experience infinite shear like fluids do. Fluidization is a solution to such problem. By bubbling a gas through solid particles fast enough, the whole system behaves like a fluid, working through varying particle sizes as well. Additionally, when solid particles are fluidized, they experience 5 to 10 times more heat transfer than they did before, meaning that our additives would melt more effectively in the plume of the lander. This diagram here shows how when relative gas velocity is high enough, it can completely convey your solid particles, treating them as one continuous fluid. Once the additive is transported down to the nozzles, thermal spraying would start to occur. In thermal spraying, a common industry practice, ceramics, metals, and polymers are conveyed onto a surface when melted in order to make that surface more resistant to wear, corrosion, and thermal degradation. Now, companies in the past, like Mass and Space Systems, have said that it may be possible to apply this technique onto the lunar surface. And with it, we hope to conglomerate regolith below the lander before PSI occurs like so. These conceptual renders we made showcase how the final integrated solution hopes to differ from harmful plume surface interactions, with the left-hand side being a normal case where PSI is occurring, and the right-hand side you can see a landing pad being formed below the nozzles of the lander due to an additive being injected into the plume from the deployment system. Now more on the additives from Aiden.
As David mentioned previously, as well as Jacoby, our solution will involve the injection of a special powder into the lander plume called an additive. This additive would ideally melt in the plume before it impacts the surface, after which it will bond with particles of regolith and solidify to form a landing pad through a process we'll often refer to as conglomeration. Through our research, we've compiled a list of candidate additives with a set of desirable properties, including a strength high enough for our landing pad to survive the strength or the forces from the plume, a landing pad less than 3,000 Kelvin, which is around the temperature that we expect the plume to be, a relatively high thermal shock resistance so that the landing pad can survive rapid changes in temperature, a high fracture toughness to ensure that flaws in the landing pad are less likely to grow into fractures, and of course, low cost and mass. So far, we have 4 main candidate additives that we are researching, and they are all common thermal spraying feedstocks. 3 of them are ceramics, and they include alumina or aluminum oxide, zirconia toughened alumina or ZTA, which is essentially just alumina with around 5 to 20% zirconia added by mass, and then yttria stabilized zirconia. We also have one main metal additive that we're considering, and that's nickel, which we have just recently begun researching after a series of successful conglomeration experiments were conducted with a particular nickel alloy that Grant here will be talking about shortly. There's also a couple other additives that we do mention in our technical report. However, we won't be mentioning them in this presentation for the sake of time, and also because they involve processes a little more complex and different from thermal spraying, and we have not assessed their viability to the same extent. However, if you are curious about any of these additives, feel free to ask us during our poster session. So here is a plot of tensile strength versus density for our main additive candidates that we obtained using the ANSYS Granta Selector database. Using plots like this, we're able to make some very rough comparisons between our main additive candidates to determine various strengths and weaknesses among each. So to kind of summarize properties from a bunch of similar plots, we have a set of single axes here to show a bunch of different properties for ease of comparison. You can see that each additive kind of has its own distinct, unique properties. With alumina and ZTA, for example, we have relatively low density and relatively low cost, but that also comes at the price of having a relatively low tensile strength and low thermal shock resistance. Whereas with zirconia, it's kind of flipped, where we have a relatively high tensile strength, a relatively high thermal shock resistance, but it's also a little bit more expensive with a density about 50% greater than alumina and ZTA. Nickel alloys, their properties can range widely, and that's because their properties heavily depend on the specific alloy content. However, one thing that remains consistent among nickel alloys is their low melting point compared to the ceramics, which means they will melt a little faster in the plume. One thing it's really important to have a diverse range of properties for our additives like this because it allows us to test the extent to which certain properties matter when forming a strong landing pad. Once we can determine the extent to which certain properties matter, we can begin to identify materials with more curated properties to better assist with this solution. Or if it turns out that the cheapest and most accessible ceramic, alumina, for example, does the job just fine, then we know we don't have to expend additional resources investing in a more curated material. So here is a bullet point summary of all of our main candidate additives, both their pros and cons. One thing that I haven't mentioned yet is that nickel is a suspected cancer hazard. And so that just means additional engineering controls will need to be considered if we implement this additive, where we'll have to ensure that the astronauts and the employees working with this additive are protected. Despite all of their respective flaws, each of these additives do have valuable properties that are worth testing to further verify and validate this unique solution for mitigating PSI.
I'm going to walk us through PARSEC's testing campaign that we conducted for verification and validation. To start off, we conducted a series of experiments in April of 2024 with the goal of trying to simulate as best we can, given funding and safety concerns, PARSEC solution on a small scale. After gaining our approval necessary by Embry-Riddle's EHS department, we moved forward with the construction of our testing rig that you can see on the right. It consists primarily of an oxyacetylene thermal spraying torch, which is specially designed to achieve high temperatures and deposit an additive on the surface below. While not precisely what our solution is suggesting, it provides a good enough baseline, especially if we saw any sort of consistent success with our testing. In total, we tested 18 different times on 3 different surfaces with 2 additives. The 3 different surfaces were sand, fire brick, and primarily our LSP2 lunar regolith simulant. Our first additive that we conducted tests with was alumina in a varying range of sizes. The additive was injected and deployed through the thermal sprayer onto the surface below. Although these tests yielded less than ideal results, with only 1 out of 8 of our tests resulting in conglomeration. Yet even that one test that formed a conglomerate was incredibly weak, and it was broken apart during our attempts to retrieve it from the testing basin. What remains is what you can see here, about a 0.11 centimeters squared section of conglomerated LSP2 and alumina. Issues that we had with this test include inconsistent flow rate thanks to the alumina clogging through our thermal sprayer feeding system, and thus we have deemed the alumina tests as inconclusive because they showed some promise, although it is primarily an issue with our deployer or our testing apparatus that led to the inconclusive results. Our second additive that we tested was Buildup 22, manufactured by Victor, and that is a nickel alloy additive. As opposed to the alumina, this additive achieved a 100% success rate in conglomeration on all 8 of our tests, conglomerating no matter the surface, whether it was directly on a fire brick, on sand, or on LSP2 regolith simulant. On the right-hand side, we can see the results from our 60-second duration test, which is also what the video is playing there. This test yielded a pad that is approximately 6 centimeters in diameter and about half of a centimeter in depth. The pad itself has fairly high strength, especially compared to the alumina tests. Additionally, supported by the fact that we have it here with us today, along with a few other samples, and they will be out at our poster session if you would like to come see them. This test and these tests of nickel alloy in particular have operated as a strong fundamental proof of concept, although we are aware more testing at scale is required to further validate the solution. This is a zoom in on one of the images on the last slide. This was taken under a microscope from our large 60-second test. Here we can see the LSP2 particulates being conglomerated by these small shiny balls of our nickel alloy additive that have clumped together and locked the particulates in place.
So to get a better idea of the stresses that a real landing pad would experience, we did develop a heavily simplified model of a landing pad and regolith bed. Using this model, we conducted static structural analysis and ANSYS mechanical, where we applied a 65 kilonewton load to the landing pad to simulate the load of a 40-ton lander. So for the model of our regolith bed, we just assume it is, the model of our regolith bed is a cylinder with a diameter of 30 meters and a 5-meter depth. And we also assume it has isotropic elasticity with an elastic modulus equal to the deformation modulus of the lunar regolith. For our landing pad, we assume that it is a particle reinforced composite, that it also possesses isotropic elasticity, that no pores, voids, or flaws are present in the landing pad structure, and that it obeys the rule of mixtures, which allows us to estimate a composite elastic modulus and composite tensile strength. So using this calculated composite tensile strength as well as the maximum tensile stress from the simulation, we're able to calculate a factor of safety. And we did this for landing pads of various sizes in an attempt to maximize our factor of safety and minimize the amount of additive mass required for the pad. We ended up finding that a pad with a diameter of 8 meters, thickness of 2 centimeters, and consisting of about 50% additive by mass had optimal properties, including factors of safety greater than 5 for all of our additives. As you can see in the bottom plot there, all those points circled in red. We have our 4 main additives, alumina, ZTA, zirconia, and nickel, where zirconia actually has a factor of safety of about 20. And for all these additives, it would require no more than 1,800 kilograms. Now, it is important to note the assumptions for this model are heavily idealized. The landing pad will more than likely have flaws, pores, and voids present if it is formed through this process that will create high stress concentrations. Nevertheless, the high factors of safety that we are seeing do show at least some promise for this solution.
This brings us to PARSEC's integration of verification and validation, or the evaluation processes used in the engineering development cycle. Both types were utilized recursively in order to ensure that at every step of the process, PARSEC meets the goals set out by NASA. Verification aims to determine that we are building our product correctly. We utilized 2 types of processes for this. The first was a test which we conducted on with alumina and nickel alloys onto a test bed of lunar regolith simulant. During our testing, it was imperative that we confirm the applicability of our product for NASA's specific needs and the intended environment. Due to constraints like cost and time, we were unable to fully replicate any real conditions. However, we were successful in our conglomeration with the nickel alloy, suggesting the potential utility of our design for future missions. We also focused on risk management, which meant addressing and combating concerning aspects of our design using both qualitative and quantitative risk assessments. Now, this will later be explained by Jacoby, but it is really important that we implement risk management throughout every subsequent stage of our process. Validation ensures that we are building the correct product. PARSEC undertook some preliminary analysis, which involved the use of a trade study to determine which mitigation method would be most likely to succeed. We compared different types based on cost, complexity, safety, and more. Once we decided on an additive injective, we then conducted 2 subsequent trade studies to determine our additive candidates and our deployer design. And to validate this system even further, we then conducted simulations and modeling using the help of both ANSYS and CATIA.
As Sanaya mentioned, the verification process, our team conducted risk analysis on our solution. To determine what risks we needed to account for our solution, we kept 4 aspects of our system in mind, being the candidate additives, deployment system, system integration, and then the space environment. Once we found 17 risks that could be posed by our design. We conducted a risk priority matrix and evaluated those risks. And from that evaluation, we found 4 of those risks to be critical. Here are those critical risks. The first one I'd like to address is the additive conglomeration performance. This risk addresses the feasibility of the additive to conglomerate the lunar regolith, because if the additive is not capable of conglomeration, then we have no landing pad formed, no PSI mitigated. And then the second critical risk I'd like to address is the additive melting properties. Just a quick note here, I did combine 2 of those critical risks into one because they both dealt with thermal properties, so that's why there's 3 critical risks instead of 4. The melting properties deal with 2 cases in the rocket plume. One, where the heat of the engine does not melt the additive enough to be an adhesive, and 2, where the additive gets melted too much and is unusable. However, we significantly mitigated these risks by coming up with successful experimental results. During testing, we have physical evidence of conglomeration, as Grant mentioned and as shown up there. So that mitigates the risk posed in the first risk and the first case of the second risk I had mentioned. Further testing will be needed to completely mitigate the risk of it melting too much. Moving on to the intermediate risk there, deployment efficiency, we address the concern that our system is vulnerable to clogging. Since we're working with a granular or powder additive, clogging is a very common problem when moving powders like that around. While we had documented this risk earlier on in the process, this risk became more apparent during testing because, as Grant mentioned, we did have a case of clogging with the 4 to 7 micron size alumina in the gravity-fed hopper. While this risk for us is mitigated since we'll be using a fluidization system instead of a hopper system, we'll need to further optimize the system to be less susceptible to clogging in the future. A thing to think about when we are optimizing, though, is adding extra mass, which leads us to our final critical risk, the system mass requirement. We determined we wanted the system mass to stay below 5% of the vehicle mass that we are using, and we are already approaching that limit with our design, so that's something we need to keep in mind. And the final risk that I will address here is the one in green, the additive health hazards. Some of the additives that we were working with are carcinogenic, and while this is a low-level risk, this is one that impacted us the most as we had to develop all new testing and safety procedures to work with them and get new safety equipment and PPE. If the Artemis program chooses to adopt this system, similar approaches will need to be taken to keep everyone safe. Moving on to the budget with Bruce.
For our budget, we use NASA's project cost estimating capability using a first pound cost estimating relationship. We derived earlier that we would need 1,800 kilograms of additive in order to develop a landing pad. This means that we would need 200 kilograms of mechanical assembly to deploy our additive and making it 5% of the lander mass. Using this, we derived that $11 million would need to be used to develop this system. We then use a non-recurring cost of 10 employees with a 50% manufacturing margin and a 30% total cost margin, again correcting for inflation, to a total of $55 million to develop this system. As for our 5-year plan, we utilize NASA's Systems Engineering Handbook to outline several major reviews that would need to be conducted, as well as a series of tests that would need to be done during phases A and phase B to further verify our solution.
For conclusion, we have found that through our PSI reduction effort that we have researched over the past year, we have tested a solution of a granular additive to be deployed onto a lunar lander and thus on the surface below. This would land and conglomerate regolith particles. For the last year, our data gathered has culminated in our testing campaign, final budget estimate, analysis, and VNV. And all of these have pointed to an attainable, realistic solution for HLS that would turn a plume of typical destruction of the surface to one of exploration by mitigating PSI and creating a rough landing pad.
Although our small-scale testing was successful, future experimentation is necessary to overcome limitations. One factor to consider is conducting comprehensive experimental assessments on larger scales in order to provide more statistical reliability. Additionally, experiments should be conducted in accurate environmental conditions. This entails conducting experiments in a vacuum-like environment with an accurate landing time, extreme temperature changes, radiation exposure, microgravity, and surface hazards such as rocks or craters. And then finally, other additives should be implemented into our testing. This includes both zirconia and ZTA. Next will come the manufacturing and full integration process, which will include vacuum, thermal, and vibrations testing. And finally, we will test on the moon. Now, our analysis and conclusions over the past year have served as a guide for future implementation. If integrated by the Artemis mission, PARSEC's innovation will aid in helping to effectively manage the risks posed by PSI, thereby ensuring the safety of future exploration. And even in 5 years, our journey will be far from over. The Artemis missions serve as a starting point for Mars and beyond. Our design can be implemented not only for the lunar surface, but for our future explorations on other planets, making it especially beneficial. Thank you.
That was right on time from Embry-Riddle Aeronautical University. We'd like to recognize their advisor, Dr. Siwei Fan. Dr. Fan, thank you. And now we'll begin the Q&A portion of their presentation with Dr. Metzger.
Okay, yeah, that was really fantastic. Your report was extremely well written, and the systems engineering was amazing. So congratulations on all that great work you did. I had one question while I was reading the report that I couldn't find the answer to, but I see you put it into the report. I was wondering if you were aware of the fast landing pad study that was massed in and later astrobotic. Were you able to get a copy of their report? Were you able to build on that work, or was it all just brand new work?
No, so we at first saw their work on their own blog on Astrobotic, I think now, and it looks like it was a bit old from 2021, and they didn't do anything with it since. And so we decided to take that as inspiration and keep moving forward with only our own work. We didn't go into ask them any questions.
Okay, you probably didn't know this, but I was a member of that project, so I do have some inside information.
So cool.
But you did a great job on the material analysis. You took it much farther than that project did. But so you said the landing pad would be 50% weight, the additive. What is the other 50%?
That would be 50% of the regolith.
Okay. Yeah, I was wondering if that's what it was. So when you did the testing with a torch, of course, that's much lower velocity than a plume. And so the droplets are going to be going much higher velocity when they hit the soil, and there will be mixing. So how would you do testing of that where you're able to get the high velocities? What would you propose to do in the future for verifying that amount of mixing?
What we would like to do is we would like to scale up these tests potentially to a lunar yard sort of scale where we can use much larger motors and then potentially prototype deployment systems, and that way we can get much more accurate at-scale measurements. That 50% that we got was from the testing that we did with the torch, and that's where we got the 50%. So it is likely that number would change, but we're not entirely sure how it would change until we do the at-scale testing.
Mm-hmm. And the other risk I could see would be, so you want to blow the material when the lander is still high enough, and so, but if you're too low and the plume is redirecting away when it hits the soil, it might just carry the droplets away. And so, have you done any analysis, plume analysis, to indicate how to prevent that from happening? What height would you need to do the injection?
To answer the question about the plume analysis, we haven't done any sort of analysis yet. That was something that was in the plan for us, but unfortunately we didn't get to do that yet. There's some literature out there on CFD analysis on thermal spraying mechanisms that are very similar to a rocket plume, but very, very much smaller scale. And so my intention was to conduct some sort of CFD analysis in Fluent, but I personally have not taken a fluid mechanics course yet, and so it was very difficult for me to get familiar with the ANSYS Fluent software, and so we unfortunately didn't get to do that yet.
Okay, thank you.
If I could add on to that question really quickly, while we were testing, we had a sample, I think it's over here. Yeah, if you can see up here, we had a sample that when we were blowing the torch, it was only a few inches away from the surface of the sand. So it was actually causing a crater. But while the crater was forming, we did get that landing pad as a result. So it may be possible to still conglomerate the surface while the plume is interacting close
How
how did you assess the effect that the plume waste products, water, heat, pressure, whatever else is in there, will have on the additives as you're injecting them into the plume? Because oxides react very differently than their parent materials.
I will say, so a lot of the additives we did choose were ceramics, and we saw that they didn't oxidize as much, but that's not something we took into account very much about the other chemicals in the plume. We were mostly focused on how it heated the additive itself.
So I'll take it that's forward work for your materials assessment. Forward work for a materials assessment.
Very much.
Okay.
We were also assuming that these materials would act fine in the plume because of their use in the industry as thermal spraying feedstocks. There are several different methods of thermal spraying. One is HVOF, or high velocity oxy-fuel spraying, which is very similar to a rocket engine.
I really enjoyed this particular proposal. I liked very innovative, a lot of very out-of-the-box thinking, so I appreciate that. Mine is kind of related to the whole conglomeration. Concerned about the adhesion, concerned we saw, especially in the case for the nickel. I'm wondering if you guys looked into any kind of, when, I don't know if you've ever done any welding or soldering, but you always use a flux. It helps with wetting the surfaces as well as improving flow. And it helps with that effect that you saw with balling. Now, I don't know at the high velocity of the plume, maybe that doesn't occur. I can't say. I'm sure Dr. Metzger could maybe elaborate on that. But I'm just wondering if you've thought about any other ways that you could improve that adhesion and improve the strength. Because I'm concerned about things like once it lands, cracking of the surface, those kind of things.
Yeah, the use of a flux is a very interesting suggestion. That's not something that we did any extensive research into.
Sorry, correction. That is actually something that we did look into. But we stopped very early on because we noticed that a lot of the other chemicals used in things like flux for soldering produced a lot of off-gassing and hazardous components that we didn't want to have to worry about, especially trying to pay attention to the safety side of it.
Okay, thank you.
Thank you, Phil, Laura, and Mark. Moving to Esther.
Hello. So I was wondering, I saw on one of your slides that you had an estimation for the deployment system mass. Would you be able to comment somewhere on that? How did you come up with that?
So the mass constraint that we came up with, it mostly came from the additive side, where we found that for a 40-ton lander, it would be around 1,800 kilograms of additive. But due to several assumptions that we'd have to make that we weren't comfortable with making yet, that would come forth with testing, we couldn't find exactly the mass of the deployment system that we wanted to. For example, my CAD model, it came under 150 kilograms, but we didn't want to just use a random CAD model for that. So we rounded up from 4.5% to 5%, assuming that 200 kilograms would be enough for that deployment system.
Do you expect any additive losses as you're kicking it out?
So from our testing, we didn't see anything being lost from, I guess, the plume of the welder. But that's something we would have to look more into with further testing, I would say.
Additionally, excuse me, that 1,800 kilogram constraint for the additive is an overestimate for how much additive is required. For the range of additives we showed, the amount of mass that's required ranges, I think, from around 1,300 kilograms to 1,700, depending on the additive that you use.
Thank you.
Good presentation, and I think good teamwork. I have a couple of questions. I noticed that your packaging, the way you package it outside of the launch vehicle. Have you considered to package it inside and actually integrate it with existing infrastructure within the launch vehicle itself, so you can share pumps, possibly tanks and heaters and things like that?
Yeah, so that's an interesting idea. Currently, we wanted to make it so that it was minimally invasive to the lander in case they already didn't want to go back on work they had already done, that it could be just fitted to any lander. The final dimensions and locations of the pumps are purposely made to be able to vary, because all you need is just the lines that would feed down to the nozzle. So it was just made to be easy to integrate.
Yeah, and if this is installed outside of the launch vehicle, then it has, as it's not within a shroud, then it has aerodynamic consequences during the launch from Earth. So that could be a big factor in terms of more motivation to be able to embed it inside the vehicle itself.
Of course. With something like Blue Moon, whether it's in a shroud or not when it launches, that could be the solution for that. But another solution or possible solution was that these could or may have to take up part of the payload space in some of these landers, and that's where they could go.
The other question I had was about the cost. There is a material cost, and there is also cost of carrying that to the surface of the moon. The cost of carrying it is several orders of magnitudes higher than material cost. The cost that you were talking about, was it overall cost, or was it just the cost of purchasing the material?
Yeah, so the full breakdown here includes development of the system. This was obtained using the project cost estimating capability. It was a first pound cost estimate where we just inputted the dry mass of the deployment system, which was the 200 kilograms. And so it does not account for that additive material cost. And then as far as transporting to the moon, I don't believe this cost is included there as well. The $11 million right there is the recurring cost, whereas the $23 million was the non-recurring that we later added to this budget. But yes, this was the output of that cost estimating software, and that was specifically for other mechanical, for general mechanical subsystems on lander type spacecraft. That was the specific CER we used.
I had a question on slide 25. I assume when you did the finite element analysis using ANSYS, you made some assumption in terms of yield, that's the stiffness of the material. So as this thing, and if you, there is a curve which you have, yield versus temperature, right? As it gets hotter, of course, you lose the stiffness and so forth. So the question I have is, how long do you have to wait for this thing to cool down? Because as it's forming, it's super hot, and eventually he has to let it cool down before he can land. And what is that time period? How long will it take to get to right temperature that he has adequate stiffness and yield that can withstand the vehicle itself?
Yeah, so that is something that we have not yet considered in our analysis. This was a very simple analysis where we were assuming that the landing pad were fully solidified at this point. And so thermal analysis would be something that we would certainly conduct later down the line to determine whether or not that will be an issue. In order to mitigate issues surrounding the landing pad cooling down and heating up, that was in our materials trade study where we were basically considering properties such as thermal shock resistance. And then also didn't show it on the slide, but we did also look at thermal conductivity of the various materials.
During your test, how long did it take before you could actually pick the sample up?
Yeah, that's what I was about to add.
Okay,
it took approximately 1.5 to 2 minutes for it to cool enough to where we could feel safe, grabbing it and moving it and whatnot.
Cool. Thank you.
Yeah.
Thank you, Esther and Jamshid. Going back to the other side of the panel, do we have additional questions?
I guess, yeah. So this is probably going to be a little hard question, but you can think real time and see if you can come up with some ideas. But so every solution to PSI has its challenges, and convincing program management is going to involve making them believe that you're reducing net risk cost effectively. So in my opinion, the risk here is that with only a 2 centimeter thick pad, less than an inch, what's going to stop that pad from breaking apart when HLS lands on it, and then the chunks of the pad become projectiles? And so that's what you've got to overcome in convincing people. What are the steps you're going to do to convince program management that this is a net reduction of risk?
So, unfortunately, we have only just recently begun looking into that problem. However, in our 5-year plan, we have tried our best to thoroughly map out any additional testing that would need to be conducted to identify these additional risks and help mitigate them by developing our pad further.
Well, can you elaborate on what would be some test activities you could do?
Some of the test activities would include, testing these materials with an actual, maybe not to full scale lander, but to a scale lander, kind of like how Astrobotics was doing, where they had the actual thruster out on a regolith bed and they were testing out in the desert. We would do the same thing. We would apply the additive and then land on it and attempt to help address that. We would also like to do additional simulations to help characterize it beforehand, just to help narrow down the range that we would be testing in.
Other questions?
Do you have in that plan, or did you look into at all the effect that the lunar environment will have on your proposed additives? For example, I have a vague memory from a long time ago that nickel tends to sublimate and then plate out on surfaces in a vacuum. So when I was reading your paper and saw nickel, I was like, no. Have you looked into that, or do you have time built into your schedule to do that?
Unfortunately, we have not looked into that, but yes, there is time built into the schedule to do that. In Phase A is additional, more in-depth additive research into these properties that we've been talking about, and in Phase B is actually testing them in vacuum environments and other similar situations.
So my question's kind of very related to what Phil had mentioned about the depth and worried about cracking and things like that. I'm wondering, any thoughts about how you can get the additive to disperse deeper into the soil or into the regolith, so that way instead of having only a 1 inch or 2 centimeter thickness, you can get it to be a thicker layer?
That's another thing we could solve with further testing. There are a couple of factors during the descent that we can control that would affect the size and shape of the pad. So if we were to, I guess it would alter the profile of the descent, but if we were to hover, that would allow us to inject more additive to increase the size of the pad or the thickness even for stability. And if we wanted to get it deeper into the pad, we could try adjusting the angle of the deployer. And that's something we had planned further testing and optimizing the deployment system, is if we wanted to add it more parallel to the engine, if that would increase the velocity, or if it was just straight up injection to the plume.
Additionally, we could look into increasing the pressure of the GN2 tank to maybe shoot out the additive even faster than the plume itself.
Relating to what Mark was saying, so on your slides you had mentioned there is an optimal pad size and thickness. I was wondering if you could give us an estimate of how long it's going to take to create that size pad.
So we didn't conduct any sort of calculations to figure out that amount of time, but that is something that we can do certainly in the future using, we could probably figure out the deposition, or I guess the injection rate of the additive into the plume, and that can probably be adjustable using the N2 pressure. But that is something that we haven't done yet, but we can certainly do in the future.
Thanks.
Other questions from the side of the panel? We have time for one question from the audience right here. Please introduce yourself.
This is Travis from Texas A&M. Have y'all thought about how your system would work for landers who don't have a propulsion system that's directly underneath them, like the SpaceX Starship?
So in regards to alternate landing methods, like where Starship have been proposed to have lander engines up near the top, we have sort of been using the assumption of using Apollo data and Apollo landers to guide us to the newer era of landers, so that if we get this solution out, SpaceX's Starship may not need the total redesign to put the engines all the way at the top. It may be able to survive with the engines at the bottom, and they can use a more simplified design. Because I may be incorrect, but I haven't heard a lot in terms of moving the engines to the top in over a year, so I don't know if that's still what they're pursuing or not.
Thank you so much, Embry-Riddle Aeronautical University team.